Do you see what I see? What do you observe about these line segments? What are their properties? How are they related? Pause the video now and capture these line segments, their behavior and relationships on paper as best you can. How did you go? Did you see 6 line segments, AB, BC and AC, as well as AB', B', C' and AC'? Did you notice that 2 of the line segments, BC and B', C' seem to be of constant length, while the other line segments clearly vary in length? Did you think that some of the line segments were of equal length? AB and AB', BC and B', and AC and AC'. The labelling of the points B' and C' does suggest this sort of connection. Did you see that the length of the line segments AB and BC could be added to obtain the length of the line segment AC? And that the same was true of AB', B', C' and AC'? To confirm these observations, some more information can be revealed. This information about the location of the endpoints of the line segments at different stages of the animation confirms our observation about the lengths of these line segments. From the information revealed, it seems that both BC and B', C' have a constant length of 3 units, even though their endpoints move. It seems like the length of the other line segments vary, and that AB and AB' are equal in length, as are BC and B', C' and AC and AC'. How did you go capturing this ever-changing diagram on a static piece of paper? Not an easy thing to do. Here are some attempts that others have made. Each attempt has dealt with the challenge of representing AB and AB', the line segments of varying length, in different ways. The broken axes symbol is used in the first attempt, looking like a bouncy spring that is capable of stretching to change its length. The second attempt has those 3 dots, which traditionally represent a process of continuing unknown length. This third attempt represents the varying length with a variable x, and contrasts it with a constant length labelled with constant 3. This makes sense because variables vary, and constants are constant. This has the added advantage of showing us that, while AB and AB' are both varying, they are varying in the same way, shown by assigning the same variable. In this way, the equality of line segment lengths has been captured. Based on that thinking, the other pair of line segments with varying length, segments AC and AC', can be labelled with the expression x plus 3, which is a varying quantity 3 more than x in length. Which of these do you like? Did you come up with any other ways to represent variation on your page? Now that we have this clever way to represent variation using a variable, as well as some other nice diagrammatic techniques, take a look at this dynamic diagram. Pause the video now and capture on paper the mathematical objects that you see and the way that they do or do not vary. So, now we have a lot more line segments, some varying in length and some of constant length. Here is a labelling that tries to capture that variation and the equality of some of those lengths. Did you do something similar? Did you see some squares and rectangles? What quantities about these shapes might we capture as constant or varying? If you haven't already, pause the video again and add some labels to your diagram to try and capture these shapes and their behaviour. Here is one such attempt. The square with constant area is labelled with its area of 3 by 3. The square with varying area is labelled with its area of x by x. And those two rectangles with varying area are labelled with 3 by x, as they have a constant side length of 3 and a varying side length of x, and hence have area of 3 by x. Now let's double up on line segment AC, reflecting C about AC dash to create the point C double dash. While we're at it, let's reflect point D about AC dash to create the point D dash, giving us this diagram. Pause the video now and add to your previous diagram. Add the new mathematical objects that have been created. What is the relationship between these new objects and the ones studied previously? How did you go with the square AC dash D dash C double dash? I have labelled its side lengths as x plus 3, based on our previous thinking about the length of AC. With that done, I have labelled the area of AC dash D dash C double dash as x plus 3 by x plus 3. Did you do something similar? How does this new square AC dash D dash C double dash relate to the object studied previously? Well, due to the nature of the points C double dash and D dash, the square AC dash D dash C double dash is a reflection of the square ACD C dash, and so these two squares must be of equal area. Square ACD C dash is made up of a square with an area of x by x, two rectangles with areas of 3 by x, and a square with an area 3 by 3. As such, the total area of square ACD C dash is x by x plus 3 by x plus 3 by x plus 3 by 3, which can be written as x squared plus 3x plus 3x plus 9, or even x squared plus 6x plus 9. Based on the equality between ACD C dash and AC dash D dash C double dash, this diagram convinces me that x squared plus 6x plus 9 equals x plus 3 all squared. A statement like this is called an identity. Mathematical identities, like this, are statements which are true for all values of x, as this one is, which we know based on the diagram from which it came. This is an example of something called the perfect square identity. Now take a look at this dynamic diagram. Pause the video now and capture on paper the mathematical objects that you see. Pay particular attention to the lengths of line segments and the areas of squares and rectangles. How did you go capturing all that variation? I used two variables, x and y, because there seemed to be two lengths that varied independently of each other, and the other lengths could be related to these two. The line segment AC dash has a length of x plus y, as its varying length is always equal to the sum of the varying lengths AB, represented by x, and BC, represented by y. The remaining line segments are either of length x, length y, or length x plus y. Did you do something similar? Now let's look at the area of those squares and rectangles that make up ACDC dash. There is still a square with area x by x, but now that BC varies with length y, there are two rectangles with area x by y, and a square with area y by y. As for the square AC-D-C double dash, its area is x plus y by x plus y. Based on the thinking that we have done about the square AC-D-C double dash as a reflection of the square ACDC dash and their equal areas, we can say, based on this diagram, that x plus y all squared, the area of square AC-D-C double dash, is equal to x squared plus 2xy plus y squared, the area of square ACDC', which is made up of that x by x square, those two x by y rectangles, and that y by y square. This identity, true for all the values of x and y that we've observed in our animation, is a more general representation of the perfect square identity. It turns out that a lot of learners of mathematics make errors by forgetting the perfect square identity. When faced with x plus y all squared, they mistakenly expand the brackets and get x squared plus y squared. This is a mistaken application of the distributive law of multiplication, which in this case is being incorrectly used to distribute an operation other than multiplication. As we know from the diagrams we have studied, this mistaken distribution omits the area of two x by y rectangles, and so in general, x plus y all squared is not equal to x squared plus y squared. To help you remember this, here is a picture of two portions of chocolate. If the perfect square identity is not considered, and if x plus y all squared was actually equal to x squared plus y squared, then these two portions would be equal in size. Which would you choose? If you keep the perfect square identity in mind, then you get two extra rectangles of chocolate in your equal portion. But hey, if you don't want that extra chocolate, I'm happy to eat it. And now, a final diagram to consider. In it, there are four independently varying lengths, labelled A, B, C, and D. With these variables, the side lengths and areas of a number of rectangles can be labelled. Have a go at doing so, and see what sort of identity arises from this diagram.